Hello everyone. So today we are going to see the problem construct binary tree from inorder and postorder traversal. So given two integer arrays inorder and postorder, where inorder is the inorder traversal of the binary tree and postorder is the postorder traversal of the same tree, construct and return the binary tree. So this is the tree. The given tree is inorder is this and given postorder is this, and finally we return this tree. Okay. Let's say these two are inorder and postorder of a tree. Okay. So now if we try to construct our tree from this inorder, let's say, what is inorder actually? Left, root, right, isn't it? So let's follow this and build a tree. Let's say this middle is our root 20, okay, then 3, then this side it's 8. I hope you are familiar with tree traversals, okay. Then at the left, 3's left is 9, then at the left is 15, 8's left is 7, and 8's right is 10, okay. So this is a tree. Now let us try to get the post order from this tree. It would be left, right, root, isn't it? This is the order. So let's do it. Left, right, and root. Now this is the left of this, right? This is the left of this root. Now we will go to right. Now in this right we will do left, left, right root. 7, 10, and 8. Now left and right for our main root is done. So now finally our root. Okay. So this is the post order of this tree. 9, 15, 3, 7, 10, 8, and 20. Okay, fine. Now the thing is, from this inorder traversal, we can construct many trees. Okay. In this case, we considered that this is the our main root. Okay, main root node, and these are our subtrees. But we can consider this one as root and this one as root, and we can form various other trees. Okay. Now we have to make a unique tree, isn't it? So if we have one type of traversals, we can construct a lot of trees. So in order to make that unique tree, we need another type of traversal, that is post order. Okay, we can have pre-order as well, but in this problem we have post order. So this is going to help us to build our unique tree. Okay, a tree whose in order would be this and whose post order would be this. Now how do we know which one is the main root of our root node of our tree? There can be we can consider any of them to be our root, right? But we don't know which one to choose particularly, so that's where our post order will help us. We know that the main root node of our tree in the post order traversal would lie in the last, right? It would lie in the last. So this is our root, main root. Okay, now this is our main root in the in order. Now here we don't know which one is the left subtree and which one is the right subtree, so that's where in order will help us, because this one is the root. Okay, this one is the left subtree and this one is the right subtree. That means this and this. Okay, so let's try to build our subtrees. Okay, in order is 9, 3, and 15, and the right subtree is 7, 8, and 10. Okay, what about the post order? 9, 15, and 3, and the right subtree is 7, 10, and 8. Okay, this is the in order and this is the post order. Now how do we know that in this subtree which one is going to be the root? That would be told by our post order. The last the last element in our post order traversal is the root. Okay, so 3 is our root. Now what about the other subtrees? This is the left and this is the right. Okay, just the way we did in the main whole array. Okay, we are breaking it down to two parts, left and right, and we are carrying out the same process. Okay, so this is the root, and here which one is the root? The last one is the root. Okay, that means this 8 is the root. Now which one is the left subtree? This is the left subtree and this is the right subtree. Okay, so we have created one more level. Now we know we need to create the left and right as well, right? So in this one, in the in order we have this. Okay, this is the in order, and in this side we have our in order, this one. Okay, now what about the post order? This is the one and this is the one. This is the left and this is the right. Okay, so for our post order, this is the left and this is the right. Fine. Similarly, in this side, this is our root. What is the left? It's 7, and what is the right? It's 10. Okay, and what about the post order? This is the left and this is the right. Okay, 7 and 10. Now let's move further. Okay, so this is our in order. Okay, now what will be the root of this subtree, it would be the last element of our post order, which is 9. So 9 would be our root. Okay, so this is the 9, this is our root. Now what would be the left subtree for this? We have nothing, that means it would be null. Okay, similarly this is the last of our post order, so 15 would be our root. So in our in-order, in both sides of 15 we have nothing, that means our child of our 15 would be null and null. Similarly here, the last one is 7, so 7 would be our root. Okay, and we have nothing on both sides in our in-order, that means they are null. Okay, similarly here, this is the root, nothing at both sides, so they will be null. Okay, so this is what our tree finally looks like. Okay, this is just the same, 23 8 23 8 9 15 9 15 7 and 10, right? So this is the idea on how we are going to build our tree from these two type of traversals. Okay, how are they helping us? The post order is giving us the root because the root lies at the last most position. Okay, and our in order is giving us the left and right when we figure out the root. Okay, now since we know 20 lies in the last position, but this 20 would lie in between this in order, right? Not in the last, but somewhere in between. So how are we going to figure out that where this root lies in our in order? Are we going to traverse again and again, again and again? Yes, we can, but a easier way would be to use a hash map. Our hash map will store the indices of the elements. So for 9 it's 0, so for 3 it's 1, for 15 it's 2, for 20 it's 2, for 20 it's 3, right? So whenever we need to find the index of our root node in our in-order traversal, we are going to access it from the hash map. Okay, what is the index of 20 in the hash map? It's 3. Okay, so we will get it in constant time. Now how are we going to apply all these operations in these two given traversals? See, initially our root was this. Okay, that is this one, and we declared that okay, 20 is our main root. Okay, topmost root. Okay, fine. Now what about the rest? What about the children? We carried out the same process in this one and this one, isn't it? Which is this and this. Okay, then from here we asked our post order, okay, for this subtree, what is the root node? This is the root node, this is the root node, and for this subtree, what is the root node? This is the root node, this, right? And then we declared them as our uh, root nodes, okay, in this level, and then we went down to this. We divided our in order to these parts, right? 7 10 9 and 15, right? We went down, then again we asked from our post order that okay, for this subtree, what is the root node? That is 9. For this one it is 15. So what are we doing exactly? We are breaking it down, right? We are following a recursive fashion, isn't it? Breaking it down to the last possible node, isn't it? So this is going to be a recursive type of algorithm. Okay, now let us write the code and we will understand everything else on the go. Okay, first of all, we need to create a hash map, right? Let's declare it globally. Why are we using this hash map? As already discussed, we are going to record the indices of each of the elements in our in order, okay, in this hash map, so we can access that index in constant time. Okay, otherwise we will have to iterate over this in order array every time, isn't it? Okay, so int n equals to in order dot length. Length of both in order and post order are same given in the constraints. So for int to 0 I less than n minus I less than n I plus plus map dot put in order of I along with its index I. Okay, fine. Now we will return our method. Let's call it build in order. Where are we starting from? We are starting from this index and this index. Okay, so 0 to n minus 1 post order 0 to n minus 1. We are now this will return our full tree. Okay, so in our full tree we are considering the whole array, isn't it? So that's why these are our parameters. Okay, now let's write this method. Private tree node, it will return the tree node, right? Build array, let's call it IO in order. The starting index, let's call it in order start, and ending index, let's call it inorder end. Okay, int post order po, int post order start, and int post order end. Okay, I hope the naming is clear. If io start inorder start becomes greater than inorder end, or our post order start becomes greater than post order end, then we will return a null. Why, we will see. This is the base condition. Okay, otherwise create the root node. Root equals to new t node. What is the root value going to be? It's going to be the last element. Okay, last element in our post order array. Okay, so initially this is our last element in the range we are considering, so that is post order end. Okay, po of post order end. Po end is the index. Okay, what is the root index in our in order? Let's call it id x equals to map.get this, isn't it? You see, our map will contain something like this: 9 at index 0, 3 at index 1, 15 at index 2, and 20 at index 3, right? So what is the index of the root, current root in our in order? It's 3, right? Instead of traversing, we are asking to the hash map that tell the index of our current root. Okay, if we know that index, then only we would be able to define this part and this part, right? That okay, if this is the index I, then the right subtree is going to start from I plus 1 and the left subtree is going to end at I minus 1, isn't it? Getting the idea? Okay, int nums at left, let's say, equals to root index minus in order start. Now what is this? See, we know the index of our root. Okay, we know that this part is the left subtree and this part is the right subtree. Now how do we know that in this post order which part is the left subtree and which part is the right subtree, isn't it? So for that we are going to calculate the number of elements in the left of our root. Okay, so it is 3, isn't it? 1, 2 and 3. So this 1, 2 and 3, these first 3 are going to be our left subtree. Okay, what would be it in index form? Our post order starts from this, right? Index 0. Now what are the number? How many numbers are in the left subtree? 3, right? So plus 3. Okay, now this is the starting index 0, post order start, and what is the end of our post order? I mean left subtree in our post order array. It is 0 plus 3 minus 1, isn't it? This is the end, right? What is this index? 0, 0, 1, 2, isn't it? If we do 0 plus 3, we reach here. This is not the ending of our left subtree, isn't it? So 0 plus 3 minus 1. Okay, that till here to index 0 plus 3 minus 1. Post order start plus number of elements in our left subtree minus 1. Okay, now what is our root dot left? Root dot left is build what? Our in order. Okay, in order start and root index minus 1. Okay, how? This is our root, this is in order start, initially it was 0, and this is in order end, right? Now what is this index? It's root minus 1, root index minus 1, isn't it? So this is the range of our left subtree in the in order array. Okay, now what about the post order? Post order, pass the array post order start, and what? This is post order start, and what is this? Post order start plus number of elements in our left subtree minus 1, right? Post order start plus number of elements nums at left minus 1, isn't it? So this is the range. In order, the left subtree is from io start to root index minus 1, io start to root index minus 1, this part. Okay, and in post order array, it's from index post order start to post order start plus nums at left minus 1. Okay, this part. Try to think about it very carefully. Okay, now this is the left subtree. Now what about the right? Root dot right is going to be build what? IO, right? Now in our in-order array, from where does the right subtree start? It starts from root index plus 1, right? From this area, isn't it? That is root index plus 1 till where? Till in-order end. What is in-order end initially? It's n minus 1. Yes, till here n minus 1, isn't it? Till here. Okay. Now what about our post order? Post order, comma. Okay, from where is our post order array, I mean right subtree starting? This was the left subtree, isn't it? This was the left subtree. Now what is this range? This index is post order start plus nums at left minus 1, right? Now what is this? Our right subtree starts from here, right? Starts from here till root index minus 1, isn't it? This one. So our right subtree starts from here. Now what is this? This index is plus 1, right? So this part gets cancelled. Post order start plus nums, isn't it? So post order start plus nums at left. Okay, this is the starting of our range, right? This one. Till when? Till here. Now what is this? This is the root index. Now what is root index actually? In our post order, it is nothing but post order end, right? If you see that, okay, what is our root node? The last element in our post order end, isn't it? So this is the post order end, and our right subtree ends at index just before post order end. So post order end minus 1, isn't it? Post order end minus 1. Fine. And finally it will recursively go to the bottom and build our tree, and it will return, and finally we will return this root. Okay, now let's talk about our base condition. Okay, see, initially our in order starts lies here and in order end lies here. Okay, post order start lies here and post order end lies here. Now with time they are coming closer to each other, isn't it? They are coming closer to each other. Okay, fine. We will be in a situation when we will be at the leaf nodes, right? This and this and this and this. Okay, this. Okay, now what do we do in our in order? What are we doing when we are at the leaf node? Both our in order end and in order start will lie in the same position, right? Now when we further call our recursion, we are going to define the left subtree and we are going to define the right subtree. So how do we define the left subtree? We say that our in order end is now going to be root index minus 1, isn't it? This one. Our in order start is in order end will be this one, isn't it? But we see that these two have crossed each other, right? They can't cross each other. They have to be in such a way that they have something in between them, isn't it? Similarly, when we call for our right subtree, we will say that our right subtree starts from root index plus 1, isn't it? Root index plus 1, that is this position, till where? In order end. In order start is here and in order end. Now where is in order end? In order end would be here, right? So we are again making them cross each other, which we shouldn't, isn't it? So that's where our things start to break. We have to stop right there. Okay, we have to stop right there. Similarly, here also this is the case. They would cross each other. Okay, that's where we stop. So this is our base condition. Okay, when in order start becomes greater than in order end, or post order start becomes greater than post order end. Okay, then at that case return a null. That, okay, we have formed the leaf node, we have nothing down below, so return a null. Now let me once more explain these parameters. Okay, these parameters for one last time. Okay, see, initially our in order start and in order end is here. Okay, and this is our root index. Now when we recursively call for our left subtree, right, left and right subtree, what is our in order end for this one, this part, this one? That is root minus 1, isn't it? Root index minus 1. And what about this? What about this part? Root index plus 1 and index in order end. Okay, now what about this? We know this is the post order end and this is the post order start. Now in this one, which one are the left subtree and which one are the right subtree? This will help us to define it. Okay, so in the left, how many elements lie in the left for our left subtree? 3. Okay, 3 elements lie. So here the first 3 elements are going to be the left subtree. So what are the indexes for it? This is the post order start. It starts from here plus 3 elements. Okay, which means index this and this minus 1, this one. Okay, so this is the range. Post order start to post order start plus 3 elements minus 1. This is the end of our left subtree. Okay, this range. Now what about the right subtree? What is this position? If this is post order start plus 3 minus 1, this one is going to be post order start plus 3. Post order start plus 3, or num set left, isn't it? Num set left. Okay, it starts from here. Till how long? Till how long? We know that this is the post order end, isn't it? This is the root node. So where is our right subtree going to end? Here, just before root node. That is post order end minus 1, isn't it? So this is our right subtree. This is how we are defining the range in our post order array. In our in order array, in order start to root minus 1, and the right subtree root plus 1 to in order end. Similarly here, from post order start to post order start plus number of elements in the left subtree minus 1. Okay, and the right subtree starts from post order start plus number of elements till post order end minus 1. Okay, I hope that is clear. If you do a dry run, okay, if you do your own whiteboarding pen and paper, things will be totally clear. Okay, so this is how we are defining the range in our traversal arrays. Okay, now what are the time and space complexities? The time complexity is going to be a big O of n to build this hash map. Okay, and a big O of n to build our tree, considering that at worst case we build a skewed tree. Okay, so our time complexity is a big O of n. Okay, now imagine we didn't have this hash map. Okay, so in that case, in each of our recursive calls, we would have had to iterate through our in order array, right, to find the root, isn't it? That would have taken a big O of n. So in that case, our time complexity would have become n square. So we created this hash map, okay, to save our indices, and we saved ourselves from this big O of n square complexity. Okay, now what is this? What is the space complexity? The space complexity is a big O of n for the hash map and a big O of n to create our build our tree. Okay, recursive stack space. Okay, this one, which is nothing but a big O of n. Okay, so I hope it's clear. This is the solution. So if you have any doubts, you can put up comments in the comment section, and if you like this video, do hit the like button, share this video and subscribe to my channel, and I will see you in the next one. Bye bye.